я запустил, как она заработала. Угу, заработала. Хорошо. Okay, so let's recall that at the previous lecture we introduced positive elements in C-star algebras and proved some basic properties of positive elements. So let's recall the definition. If A is a C-star algebra, then we say that an element little a is positive, and we use the following notation. If it is self-adjoint, first of all, it is self-adjoint, and second, the spectrum of this element is non-negative. Well, since we don't assume that A is unital, we must take the non-unital spectrum here. But if A is unital, then we can replace this by the usual spectrum. So this is equivalent to the following inclusion in the case where the algebra is unital. Because in the unital case, the non-unital spectrum is just the union of the spectrum and the single point, namely 0. So these two conditions are equivalent in the unital case. And let's recall some facts. So first of all, a notation. We use the following notation for the set of all positive elements in our algebra. Well, for example, if A is the algebra of continuous functions on a compact Hausdorff topological space, then, well, first of all, we know that a function is self-adjoint if and only if it is real. And it's also clear that a function is positive in this sense if and only if it is everywhere non-negative. Morally, we think of self-adjoint elements of a C-star algebra as real elements, as generalizations of real-valued functions. And we think of positive elements as generalizations of non-negative functions. That's the idea of this notion. Okay, so what do we already know about positive elements? Let's recall the following facts. First of all, we know that if little a is positive and lambda is a real non-negative number, so let me write down this like this. So A is positive, lambda is a non-negative real number, then lambda A is also a positive element. This is clear from the definition. What is not entirely clear, but what was proved at the previous lecture, is that the sum of two positive elements is positive. If A1 and A2 are positive, then their sum is also positive. And we also observe that the following formula holds. So this intersection is 0. In other words, if an element little a is positive and minus a is also positive, then a is 0. So these properties together actually mean that the set of positive elements is a cone, is a convex cone in A. Moreover, this cone is closed. We proved that the set of all positive elements is closed in A. We have also discussed square roots. We proved that for every positive element in A, there exists a unique positive element denoted like this, such that this element squared equals A, so-called the positive square root of A. And this element was constructed explicitly. We just take the function square root of t, where t is just the inclusion of the spectrum of A into the complex plane, and apply it to A. So we use the functional calculus for our element. And we also observed that every self-adjoint element can be written as a difference of two positive elements. So for every self-adjoint element little a, there exists a unique pair A plus, A minus of positive elements such that A is A plus minus A minus, and the product is 0. A plus A minus equals A minus A plus, and this is 0. And let's recall that this pair was constructed explicitly with the help of functional calculus. So we considered the following two functions. This is the function t plus. This is the function t minus. And we defined the elements A plus and A minus in the following way. So we simply apply these two functions to our element A. And these elements are exactly what we need here. In fact, it's rather obvious that these two elements satisfy these conditions. So what is not entirely obvious, and this was proved at the previous lecture, is that such a pair is unique. It is unique. Okay, so this is a summary of what we already know about positive elements. Our next goal is to prove the following fundamental result about positive elements. This result is due to Irving Kaplansky. It was proved in the 1950s. I don't remember exactly the year, something like 1952 or 53. He proved that for every element A in our C-star algebra, the element A star A is positive. Historically, this theorem was not a theorem. Actually, this was an axiom. This was a part of the original definition of a C-star algebra. It was given by Gelfand and Nymark in 1943. And actually, Gelfand and Nymark observed already in their first paper, they observed that, they didn't observe, but they conjectured that maybe this axiom actually follows from other C-star algebra axioms. But they were unable to prove this, but they conjectured that this is true. And indeed, it turned out 10 years later that, that this is indeed true. So this property holds in any C-star algebra. So the original axiom given by Gelfand and Nymark is actually redundant. This follows from the C-star algebra axioms. The proof will be based on a couple of lemmas. Lemma 1. So I claim that for every element x in A, the element x star x plus x star is positive. To prove this result, we decompose x into the real and imaginary part. So we can write x in the form y plus I z, where y and z are self-adjoint elements. Then x star equals y minus iz. And we simply calculate So x star x, what is this? This is y squared plus z squared plus I yz minus zy. And if we multiply them in the opposite order, x star, then this equals y squared plus z squared plus I zy minus yz. So we now take the sum of these elements, and what we get x star x plus x star equals 2 times y squared plus z squared. And the remaining terms cancel. And this is positive. Why is this positive? Y squared and z squared are positive by the properties of the functional calculus. Well, if we have, let's recall that another fact which was observed at the previous lecture, if we have a continuous non-negative function on the spectrum, then f of a is positive. Here a is any normal element. This follows from the fact that the functional calculus is a star homomorphism, and a star homomorphism always takes positive elements to positive elements. So since f was a positive element in this algebra, we conclude that f of a is a positive element in our algebra A. So now f of a is just a squared here. F of y is y squared, f of z is z squared. These functions are positive, so this element is positive. The sum of two positive elements is positive. We multiply it by 2, and we still get a positive element. So this element is positive. And this completes the proof of lemma 1. Lemma 2. Lemma 2 is actually purely algebraic. It is not about C-star algebras. It is about arbitrary unital algebras. Suppose that A is a unital algebra. And A and B are two elements of A. I claim that the spectrum of AB is almost equal to the spectrum of BA. What do I mean by almost equal? I mean that if we add 0, then these two sets are the same. By the way, it's quite easy to understand why we have to add 0. If we, for example, consider the right shift and the left shift operators, say on the little L2 space, then AB is 1, but BA is not 1, and BA is not invertible. So in general, the spectrum of AB is not equal to the spectrum of BA, but if we add 0, then the resulting sets will be identical. The proof is purely algebraic. First of all, observe that it suffices to show that 1 minus AB is invertible if and only if 1 minus BA is invertible. If we prove this equivalence, then this will imply the lemma, because for every non-zero number lambda, the element AB minus lambda, which appears in the definition of the spectrum, can be written as minus lambda times 1 minus lambda inverse AB. And this element, clearly this element is invertible if and only if this element in brackets is invertible. And so everything is reduced to this equivalence. Okay, so, well, let's suppose that one of them is invertible. Say 1 minus AB is invertible. And let's C denote the inverse element. Then, and this is a straightforward computation, and this is an exercise for you, the element 1 plus BCA is the inverse of 1 minus BA. Well, just substitute it, this element, just calculate explicitly 1 plus BCA times 1 minus BA. So the result will be 1 in any order. So formally, this is the end of the proof. The only question which naturally appears when we look at this proof, how can we guess this formula? So let me briefly give an informal explanation for this formula, which explains where it comes from. Informal explanation. So we look at 1 minus AB and assume that A and B are small. Say the norm of A and the norm of B is less than 1. In this case, the norm of their product is less than 1, and we can explicitly calculate the inverse as the sum of the progression and so on. 1 plus AB plus AB, AB, and so on. So we want an explicit formula for the inverse of 1 minus BA, and this will be 1 plus BA plus BA, BA plus BA, 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 and so on. And now we do the following. We write 1 plus B times something and times A. So what do we have in brackets? Well, 1 plus, here we have just AB. Here we have this element, AB, AB, and so on. So we see that the expression in brackets is equal to this one. And so we get 1 plus BCA. Of course, this is not a proof, because we have assumed that A and B sits in the Banach algebra and they are small. Lemma itself is true in any unital algebra and for arbitrary elements A and B, but at least this little calculation explains where this formula comes from. Okay, now we are ready to prove our theorem. Proof of theorem. So let's denote by B our element A star A. We want to show that B is positive. So we write B as B plus minus B minus, just like in here, in this formula. So B plus and B minus are positive, and the product is 0. B plus B minus equals B minus B plus equals 0. So we want to show that B minus is 0. We want to show that B minus is 0. Let's denote by X the following auxiliary element. X equals A, B minus. Then, what is X star X? X star X is, well, X star is B minus A star A B minus. A star A is B, and B is B plus minus B minus. So this is B minus times B plus minus B minus times B minus. The product of B plus and B minus is 0, so the result will be just minus B minus cubed. B minus is positive. B minus is positive. By the functional calculus, B minus cubed is also positive. So this calculation implies that the element minus x star x is positive, because it is equal to B minus cubed. Okay, let's now look at x star. So we want to apply lemma 1 somehow. Where is it? Lemma 1. So to apply lemma 1, we must calculate x star and use the fact that this sum is positive. So what is x star? We can write x star as follows. This is x star x plus x star plus minus x star x. Now, lemma 1 implies that this bracket, this expression in brackets is positive. This one is positive by lemma 1. But we have just proved that this one is also positive. So their sum is positive. This is a sum of two positive elements, and this is positive. X star is positive. So the spectrum of this element sits in the non-negative half line. But we can now apply lemma 2. Lemma 2. The spectrum of the element x star x is essentially the same, modulo 0. So this implies that x star x is also positive. X star x is also positive. Well, but we already know that minus x star x is positive. So these two elements are both positive. This can happen only if this element is 0. This implies that x star x is 0. But x star x is minus b minus cubed. So we conclude that b minus cubed is 0. Finally, we take the cubical root, apply this root, and we get that b minus is 0, just by the superposition property. Let's recall that the superposition property for the functional calculus tells us that the following formula is true. If A is a normal element of a C-star algebra, G is a continuous function on the spectrum of A, and F is a continuous function on the spectrum of G of A, then we can apply first G to A, then F to G of A, but the same result, we get the same result if we first compose F and G and then apply their superposition to A. So this is the superposition property for the functional calculus. Here we apply this property to the two functions. F of t is t cubed and g of t is this root. So we conclude that b minus is 0, and so b is positive. B equals b plus, and so it is positive. And this completes the proof. So we see that the proof is quite short, but rather tricky. So the trick is to consider this element, which is not entirely obvious. Probably this is the reason why this result was proved only 10 years after the first Gelfand-Naimark paper. Okay, let's now consider some simple applications of this result. As the first application, we can now define the absolute value of any element in a C-star algebra. So we introduce the following notation. For every element A in our C-star algebra A, we denote like this. the absolute value of A, the square root of the element A star A. So this is well defined because A star A is positive. By the way, let's observe that in the case where A is self-adjoint, this notation is consistent with the functional calculus. If A is self-adjoint, then the absolute value of A is equal to the square root of A squared. And by the superposition property, this is nothing but the function, the absolute value of t applied to A. Because the square root of t squared is the absolute value of t. And so, in terms of our elements A plus and A minus, if we add these elements, if we write A plus plus A minus, this is nothing but the sum of these two functions applied to A. That is the absolute value of t applied to A. So we see that this is nothing but A plus plus A minus. But the point of this definition is that this works for any element, not necessarily self-adjoint, and even not necessarily normal. Okay. As another application of Kaplansky theorem, we get the following nice characterization of positive elements. Corollary. So let little a be an element of our sister algebra A. Then the following conditions are equivalent. Condition 1, A is positive. Condition 2, there exists an element, a positive element B, such that A equals B squared. Condition 3, there exists a positive element. Oh, sorry, there exists a self-adjoint element B, such that A equals B squared. And finally, condition 4, there exists an element B in A, such that A equals B star B. Well, indeed, why is it so? 1 implies 2, because we can take the square root of A, and it is positive. Well, clearly 2 implies 3, and 3 implies 4. This is just trivial. And now Kaplansky's theorem shows that 4 implies 1. And that's it. Now, by using the notion of positivity, we can now introduce the following useful order relation on our sister algebra, or more exactly, on the set of all self-adjoint elements in A. So we give the following definition. Suppose we have 2 self-adjoint elements, A and B. We say that A is less than or equal to B if B minus A is positive. Well, again, in the commutative case, in the case where A is the algebra of continuous functions on a compact topological space, this is just the usual order relation for real-valued functions. So what can we say about this relation? I have the following proposition. First of all, this is indeed an order relation. So the set of all self-adjoint elements together with this relation is a poset, a partially ordered set. Second, if A is less than or equal to B, and lambda is a non-negative real number, then lambda A is less than or equal to lambda b. Property 3 is that this relation is compatible with the additive group structure on the set. So if A1 is less than or equal to B1 and A2 is less than or equal to B2, then A1 plus A2 is less than or equal to B1 plus B2. Property 4 looks as follows. If A is less than or equal to B, then for every element x in our algebra, the element x star ax is less than or equal to x star bx. So we can multiply by x on the right and by x star on the left, and we have the same inequality. Property 5, if our algebra is unital, B is a self-adjoint element, and it is greater than or equal to 1, then B inverse is less than or equal to 1. So the operation of taking the inverse is order reversing. Property 6, which is more general than property 5, if A and B are two positive elements, such that A is less than or equal to B, and if they are invertible, A and B are invertible, then B inverse is less than or equal to A inverse. Actually, this is more general than property 5, but it will be convenient first to prove property 5 and then to deduce property 6. By the way, I have to say that here B is automatically invertible because it is positive. Oh, sorry. Sorry, of course. Okay, yes. We assume that B is self-adjoint in greater than or equal to 1. So this means that the spectrum of B sits in the half line from 1 to 2 plus infinity. So in particular, the spectrum of B doesn't contain 0. So B inverse is well defined. And here we assume that A and B are invertible. Property 7 tells us that the norm is a monotone function on positive elements. If A and B are positive and A is less than or equal to B, then the norm of A is less than or equal to the norm of B. And another useful property, property 8, if A is a positive element of A, then the norm of A is less than or equal to 1, if and only if A itself is less than or equal to 1. In the general case, we consider the identity of the unitization of our algebra, but if A is unital, this is equivalent to the property that A is less than or equal to 1 in the algebra itself, if A is unital. Well, why is it so? Actually, parts 1, 2, and 3, 1, 2, and 3 follow from the general properties of positive elements. 1, 2, and 3 follow from properties of positive elements. In particular, the relation, our order relation, is transitive because the sum of two positive elements is positive. If A is less than or equal to B and B is less than or equal to C, then B minus A and C minus B are positive. Their sum is C minus A, so C minus A is positive, and so A is less than or equal to C. So it is transitive. And similarly, one easily proves 2 and 3. So this follows from the fact that the set of positive elements is a convex cone. Okay, property 4 follows from Kaplanski's theorem. So b minus a is positive. So we can write b minus a. If we can write b minus a in the form c star c for some element in our algebra. For example, we can take c. We can take the square root of b minus a. And then x star minus x star bx minus x star ax. This is x star b minus a x. That is x star c star cx. That is cx star cx. And by Kaplanski's theorem, this is positive. So this proves part 4. To prove part 5, it is convenient to just apply part 4 to apply 4 in the case where a equals 1 and x equals b to the power minus 1/2, if I'm not mistaken. Yes. Oh, well, just a moment. Sorry about this. Just so b is greater than or equal to 1. So we let a equal 1, and this is true. And then we take b minus 1/2 here, b to the power minus 1/2 here, and the result here will be 1. So we get b inverse is less than or equal to 1. Okay, this seems to be correct. Minus 1/2. And that's it. So this gives us part 5. Part 6 is deduced from part 5 as follows. So a is less than or equal to b. We multiply it by a to the power minus 1/2 on both sides, and we get the following. This follows from property 4. Property 4. Now we apply property 5 to this element, which is greater than or equal to 1. So the inverse of this element is less than 1, while the inverse of this element looks like this. This is less than or equal to 1. And again, we apply 4. We multiply on both sides by a to the power minus y/2. And we get b inverse is less than or equal to a inverse. Good. So this proves part 6. Part 7. The best way to prove part 7 is to reduce everything to the case where we work with continuous functions. That is to apply the first Gelfand-Deinberg theorem. Well, indeed, first we forget about a, look at b, and apply the first Gelfand-Deinberg theorem to the C-star subalgebra of A, or better of A plus, since we don't assume that A is unital, generated by B and the identity. So this is a commutative C-star algebra, unital, so it is isomorphic to the algebra of continuous functions on a compact space, that is on the spectrum of B. And we conclude that we have the following inequality, which is obvious because we work with continuous functions. So if B is a continuous function, which is between 0 and 1, then of course it is less than or equal to 1. And in general case, it is less than or equal to 1 multiplied by its supremum norm. So this is obvious because we work with continuous functions. Now we use the transitivity of our order relation, and we conclude that A is less than or equal to the same element by transitivity. And now again we apply the Gelfand-Naimark theorem, but this time to the algebra generated by A and the identity. So we apply the first Gelfand-Naimark theorem to C-star subalgebra of A generated by A and the identity. So these elements sit in this subalgebra. It is also isomorphic to the algebra of continuous functions, and we conclude that the norm of A is less than or equal to the norm of B. Okay, and so this proves part 7. And finally, oh yeah, 1 plus, thank you. If A is unital, we can take 1, but since we don't assume that A is unital, we consider the identity of the unitization way. Okay, and finally, part 8 is also proved by means of the Gelfand-Naimark theorem. Indeed, we apply this theorem to the C-star subalgebra generated by A and the identity, or in the unital case, to the C-star subalgebra generated by A and the identity of A, if A is unital. So this algebra is commutative, and again, in commutative C-star algebras, that is in algebra of continuous functions on compact Hausdorff spaces, property 8 is trivial. A positive function is less than or equal to 1 if and only if it is norm, if and only if its norm is less than or equal to 1. Вначале мы применяем теорему здесь и получаем вот это. Потом пользуемся тем, что они происходят b, и получаем вот это. А потом смотрим, это число умноженное на единичку, а это элемент. Они все, вот эти оба элемента, они сидят в этой алгебре. И этот, и этот. Мы когда к этой подалгебре применяем теорему Гельфанда-Наймарка, мы получаем алгебру непрерывных функций, значит, это непрерывная функция, а это непрерывная функция умножить на единичку. Ну, раз в непрерывной функции не происходит константа умножить на единичку, то ее норма не происходит этой константы. Вот она положительная, не отрицательная эта функция, поэтому вот так. So, basically the idea is that if we take a convenient commutative C-star subalgebra, then our problem reduces to a problem about continuous functions. And for continuous functions, this implication is trivial. And this one is also trivial. And the same phenomenon appears in 8. So we just replace A by the C-star subalgebra generated by A and the identity. This is the algebra of continuous functions. And clearly, if we have a continuous function which is non-negative, then this function is less than or equal to 1, if and only if its norm, its supremum norm, is less than or equal to 1. That's it. So this is a good demonstration of the power of the Gelfand-Naimark theorem. Some parts of this proposition can be proved without using the Gelfand-Naimark theorem, but the proof will be essentially more complicated. But the Gelfand-Naimark theorem simplifies the proof a lot. Okay, so these are the basic properties of our order relation. Our next goal is to discuss approximate identities in C-star algebras. Approximate identities. Well, first of all, let me say just a few general words. We know that many natural C-star algebras are not unital. Maybe this is not very convenient, but this is life. Algebras of compact operators, algebras of C0 functions, and actually there are many other natural examples of non-unital C-star algebras. Sometimes, to work with such algebras, it suffices to add an identity, that is to consider the unitization of our algebra, and in many cases this solves all problems. But it turns out that there are situations in which we have to work in the original C-star algebra, not in the unitization, but in the original C-star algebra. So the notion of an approximate identity, which we are going to introduce now, is a reasonable analytic substitute for an identity. Before we define approximate identities, let me say a few words about nets in topological spaces. Suppose that we have a partially ordered set, lambda, a pose set. Let's recall the following definition. We say that lambda is directed if for any two elements lambda and mu in the set, there exists another element nu which dominates both lambda and mu, such that the following two inequalities hold. Well, two typical examples to keep in mind is, of course, the set of all natural numbers with the standard order. Clearly, it is directed, and in fact, any other totally ordered set is directed. And another typical example is the following. We start with a topological space X. A topological space. We take a point, little x, and we denote by lambda the collection of all neighborhoods of this point. All neighborhoods of X. The order relation is the opposite inclusion. And this set is easily seen to be directed, because if we have two open neighborhoods of a point, then their intersection is also a neighborhood, and it dominates U and V, both U and V, in the sense of this order relation. Okay, now let's introduce nets in topological spaces. So from now on, we assume that X is a topological space. By definition, a net in X is an arbitrary map, little x, from lambda to X, where lambda is a directed pose set. Lambda is a directed pose set. By the way, in the Russian literature, we usually say направленность. Иногда говорят сеть, но по-английски net, а в русской литературе чаще говорят направленность. Что, кстати, лучше отражает суть дела. Но это только в русскоязычной литературе. So in the English literature, we always say a net. When we work with nets, it's convenient to use the following notation, which reflects the fact that a net is a generalized sequence. So we think of a net as a family of elements indexed by the points of lambda. So x sub lambda is just x evaluated at lambda. Of course, in the case where lambda is the set of natural numbers with the usual order relation, what we get is just a sequence in a topological space. So roughly, nets are generalized sequences. Given any net in a topological space, we may define the notion of convergence in exactly the same way as the notion of convergence for sequences. We say that a net x lambda converges to a point little x, and write the following combination of symbols. Or we can also write that the limit of this net is equal to x. If for every neighborhood of this point, for every neighborhood u of x, there exists a number lambda 0, that is an element of our set lambda, such that whenever little lambda is greater than or equal to lambda 0, we have the following inclusion: x lambda belongs to u. So literally the same definition as in the case of sequences. And here's a typical example. Let lambda be the partially ordered set from our example 2. That is the collection of all neighborhoods of a fixed point, little x. The partially ordered set from example 2. So we take any u in this set, this is the neighborhood of x, and choose an arbitrary point in this neighborhood. Choose any xu belonging to u. Then we trivially have the following convergence. xu converges to x, just by the very definition of a convergent net. This is, maybe this is trivial, but this is useful. Let's use, for example, when we work with arbitrary nets in topological spaces. Okay, let's now introduce approximate identities. From now on, we suppose that A is a normed algebra. A normed algebra. By definition, an approximate identity, and we usually abbreviate this as AI. An approximate identity in A is a net E lambda A, such that for every element little a in our algebra, we have the following convergence. A E lambda converges to A, and E lambda A converges to A. In some sense, we think of E lambda as a net which converges to the identity. But the identity doesn't exist. So actually, E lambda doesn't converge. But after we multiply E lambda by an arbitrary element A, we have this convergence. That's the idea. Sometimes it is convenient to consider approximate identities with some specific properties. We say that an approximate identity E lambda is sequential property 1, E lambda is sequential. If it is a sequence, that is, if lambda, the set lambda is the set of natural numbers with the standard order relation. And another useful property, we say that E lambda is bounded if the set of all these elements E lambda is bounded. That is, if there exists a constant C such that the norm of E lambda is less than or equal to C for every lambda. Let's look at some concrete examples of approximate identities. Example 1. Let's take the algebra little c0 of sequences vanishing at infinity. So its elements are complex sequences such that the sequence vanishes at infinity. So in other words, this is big C0 of n, where n is equipped with a discrete topology. And for every natural number n, let En denote the following sequence. So we have n identities and a long tail of zeros. I claim that En is a bounded approximate identity in C0. By the way, it's clear that C0 is not unital. C0 is not unital, so the sequence which is identical to 1 doesn't belong to C0. But this example shows that this algebra has a bounded approximate identity. And to see this, we just take, so indeed, we take any element little a in little c0, and we calculate the norm of a minus aen. So what is this? This is just the supremum of the tail, ak, where k is bigger than n. And clearly this goes to 0 because an goes to 0. So this is a bounded approximate identity. Example 2 shows a difference between bounded and unbounded. Suppose now that A is the little L1 space of absolutely summable sequences. So it is a Banach algebra with the pointwise multiplication. So the multiplication is the same as C0. So we simply multiply A. If we want to multiply A by B, we write A1 B1, A2 B2, and so on. We can take the same sequence as here and observe that the same argument shows that En from example 1 is an approximate identity, but this identity is not bounded. It is an unbounded approximate identity in L1. Because the norm of this element is equal to n. Can we find another approximate identity which is bounded? The answer is no, and this is a useful exercise. L1 doesn't have a bounded approximate identity. Example 3 is a natural continuous analog of example 1. Let's take the algebra of continuous and vanishing at infinity functions on the real line. Again, it's clear that this algebra is not unital, but it's rather easy to construct a bounded approximate identity here. Namely, let me just draw a picture. We denote by En the following function, which is identically 1 between minus n and plus n, identically 0 here and here, and linear on these two intervals. So this is En. And it's a simple exercise to show that En is a bounded approximate identity. In C0 of R. The proof is basically the same as in example 1. Actually, this example can easily be generalized to an arbitrary, locally compact Hausdorff topological space. Example 4. Example 4. Let X be a locally compact Hausdorff topological space. And let lambda denote the family of all compact subsets of X. Family of all compact subsets of X. And we make lambda into a directed poset with respect to the inclusion. Clearly it is directed because the union of two compact sets is compact. Now we choose for any k in lambda, for any compact subset of X, we choose a function ek in C0 of X in such a way that this function is, the restriction of this function to k is identically 1, and such that the norm of this function is less than or equal to 1. The existence of such a function easily follows from Urysohn's lemma. Actually, we can take a compactly supported function with this property. And moreover, we can assume that ek is in C0 of X. Then again, a simple exercise is to show that ek is a bounded approximate identity in C0 of X. Well, of course, in contrast to example 3, this approximate identity is not sequential in the general case. So the natural question is, can we find a sequential approximate identity in this algebra? And here's an answer. C0 of X has a sequential bounded approximate identity, if and only if X is sigma compact, which means that it is a countable union of compact sets. Example 5. So far, all our examples were commutative. Let's now look at a non-commutative example. Let H be a Hilbert space, and let A be the algebra of compact operators, the algebra of compact operators on H. It's well known that if H is infinite dimensional, and we assume that H is infinite dimensional, then this algebra is not unital, because the identity operator is not compact. However, it's rather easy to construct a bounded approximate identity in this algebra. Indeed, let lambda denote the collection of all finite dimensional vector subspaces. Finite dimensional subspaces. Say L in H. And we make lambda into a directed poset with respect to the set theoretic inclusion. Clearly, this set is directed because, well, if we have two finite dimensional subspaces, then their algebraic sum is also finite dimensional. And now we construct our net. So for every finite dimensional subspace L of H, we let P lambda denote the orthogonal projection. The orthogonal projection onto L. So this is a finite rank operator. In particular, it is compact. And I claim, again, this is an exercise for you, that the resulting net PL is a bounded approximate identity. Is a bounded approximate identity in K of H. Well, we can ask the same question as in the previous example. Can we find a sequential approximate identity? And here's an answer, which is also an exercise for you. K of H has a sequential bounded approximate identity, if and only if H is separable. Okay, so by looking at these examples, we see that in many, well, not in many, but in the basic examples of non-unitary sister algebras have bounded approximate identities. So C0 of X has a bounded approximate identity, and K of H has a bounded approximate identity. And what we are going to do now is to show that actually any sister algebra has a bounded approximate identity. I have the following theorem. So suppose that A is a sister algebra. Then there exists an approximate identity, E lambda, in A, satisfying the following conditions. An approximate identity is such that, first of all, each element in this net satisfies the following inequality in A plus. So each E lambda is positive and is less than or equal to 1. Or equivalently, this means that equivalently E lambda is positive and the norm of E lambda is less than or equal to 1. So we already proved today that E lambda is less than or equal to 1 plus, if and only if its norm is less than or equal to 1. So this is an equivalent condition. And condition 2 is that this net is monotone. If lambda is less than or equal to mu, then E lambda is less than or equal to E mu. So in particular, condition 1 implies that this is a bounded approximate identity. It is bounded by 1. Well, to prove this result, we first have to construct the respective partially ordered set, the index set for our net. This index set lambda will consist of all positive elements E, all positive elements E, such that the norm of E is strictly less than 1. So clearly this is a is a partially ordered set with the usual order relation, which was introduced today. This is a pose set. But what is not entirely obvious is that this pose set is directed. Actually, I claim, and this is the first step in the proof of our theorem, that lambda is isomorphic, is order isomorphic to the set of all positive elements. These two ordered sets are isomorphic. And this the existence of this isomorphism already implies that lambda is directed. Because the set of all positive elements is clearly directed. If we have two positive elements A and B, then each of them is dominated by A plus B. And so if we prove that they are isomorphic, this will imply that lambda is also directed. Well, proof of claim 1. We explicitly construct this isomorphism from the following idea. First, we construct an order isomorphism between the interval 0, 1 and the interval from 0 to plus infinity. Что? Не, я про это говорю. Вот это, this set is clearly directed. And if we prove that they are isomorphic, then this will be also directed. But I don't claim that the sum of two positive elements in lambda belongs to lambda. This is not true. If we have two elements in lambda, they will be dominated by another element, but not by their sum, but something different. So we start by constructing the following picture. We construct a very simple order isomorphism between these two subsets of the real line. So let me draw a picture. This is phi, and this is psi. So explicitly, phi of t is 1 minus 1 over 1 minus t. Yes, this is, it takes 0 to 0, so this is correct. And psi is the inverse function, and it is given by 1 1 over 1 plus s just a moment. What was the question? Not exactly this, but 1 plus s 1 minus this. Is this correct? Huh?
So phi takes 1 to minus infinity.
Phi takes 1 to infinity? We want it to be positive. Well, it is positive. What's the problem? It is defined on the half interval. It is not defined at 1.
So if t is a bit smaller than 1, then...
If t is a bit small, so good. Thank you. Thank you. Like this. So this is better. Yeah? Isn't it? Well, it is. We want it to take 0 to 0. It indeed takes 0 to 0. It is positive. Is it? Yes, it is. It is positive. Yes, and it tends to infinity when as t goes to 1. And is this correct? 1 plus s. This is s. 1 plus s is 1 over 1 minus t. So 1 minus t is 1 over 1 plus s. Good. Seems to be correct. Okay. So how do we use these functions? Well, we simply apply the functional calculus. What if we apply phi to an element in our set lambda? Well, let's observe that for every element E in lambda, what can you say about phi of E? First of all, I claim that this belongs not just to A plus, but to A. A is not assumed, of course, A is not unital, but we know that the functional calculus takes an element to itself if it vanishes at 0. But phi vanishes at 0, so phi of E sits in A. And moreover, it is positive because the function phi is non-negative. The spectrum of E sits somewhere on this interval, somewhere here, and so phi is non-negative. So phi of E is positive. Okay, let's now observe that phi preserves the order relation. So suppose that we have two elements, E1, E2 in lambda, such that E lambda is less than or equal to E2. Then 1 minus E2 is less than or equal to 1 minus E1. We now use one of the properties of our order relation, which tells us that, in this case, 1 minus E1 inverse is less than or equal to 1 minus E2 inverse. We have already proved this today, that if A is less than or equal to B, then B inverse is less than or equal to A inverse for any pair of positive elements A and B. And when we look at phi of E, this is 1 minus E inverse minus 1, we conclude that phi of E1 is less than or equal to phi of E2. So phi preserves the order relation. Now let's look at psi. If we take a positive element A and apply psi to A, I claim that psi of A will belong to lambda. Well, indeed, why is it so? Again, psi vanishes at 0, so it takes A to itself. The set of all, not just A, but the set of positive elements goes to A. So this element belongs to A, and it is positive because the function psi is positive on the spectrum of A. And why does it belong to lambda? Well, the norm of psi of A is just the supremum of psi over the spectrum. But clearly the supremum of psi over the spectrum is strictly less than 1. So the norm of psi of A is strictly less than 1. And so this means that psi of A belongs to lambda. The same argument, a similar argument, shows that psi preserves the order relation. If A1 is less than or equal to A2, then psi of A1 is less than or equal to psi of A2. This is a little exercise, but this is absolutely similar to the previous line. So as a result, we get two maps, basically the same psi and psi, but now they act between lambda and the set of all positive elements. Each of them preserves the order relation. And now we just apply the superposition property for the functional calculus, which implies that psi composed with phi is the identity map on lambda, and phi composed with psi is the identity map on the set of all positive elements. Just because this is true on numbers. The superposition of phi and psi is the identity map. And so the properties of the functional calculus imply this and this. So we conclude that phi and psi are order isomorphisms. They are inverse to each other. And so these two sets are order isomorphic. And this completes the proof of claim 1. Okay, so at this point, I just present our net, and the rest of the proof will be given at the next lecture. And the construction of the net is very easy. The inclusion map, we denote by E, the inclusion map of lambda into A. And this is, obviously, this is a net in A. And what we will be proved at the next lecture is that this net is actually an approximate identity. So clearly it satisfies, the net satisfying our two conditions, 1 and 2. 1 and 2. And at the next lecture, at the beginning of the next lecture, we will show that this is indeed an approximate identity. Okay, so that's all for today.